Okay, let's get started. Okay, this is a MAE 297 seminar. Today we have a seminar presented by Professor Rida Farouki. He's a professor here at UC Davis, working in the area of the computer-aided design, the computer-aided manufacturing. His topic is about spatial Pythagorean-hodograph, Quaternions, and the rotations R3 and R4. When I was a graduate student back in more than 20 years ago, I have read this about the quaternions. My professor told me the quaternion is invented by Hamilton, with a lot of good stories. I think Rida is going to talk about it. It was classified as the Irish strategy because Hamilton could spend all his time doing much greater thing, but he spent all his time on the quaternion. So now I want to see what is. However, we have been seeing a lot of the work, and I myself also devote some of the time on this quaternion things. Actually, before I came here, there's a professor here called Andy Yan. He is well known for his work using the dual numbers and the quaternions. So it looks like UC Davis is going to have a tradition on this quaternion and its applications. With all this introduction, I think turn the floor to Rida.
Okay, thanks, Harry. As engineers, we are all familiar with vector analysis, but we get very little exposure to what are called quaternions. As a matter of fact, many people lead productive lives as engineers and scientists without ever hearing about quaternions. A couple of years ago, I was asked to give a talk at a meeting of community college math teachers at American River College. And the person who asked me was a former graduate student here at UC Davis. And he specifically asked me to talk about quaternions. And after I finished the talk, I was amazed at the number of people who approached me and said, I've never heard of quaternions before. What is tragic, really, about this topic is that vector analysis, as we know it, comes from the theory of quaternions. And the person who invented quaternions, as Harry said, Hamilton gets no credit for it. It's not an unusual circumstance in scientific research, actually. I'll begin this talk by explaining why I was motivated to study quaternions. They arise in constructing a special class of curves that I'm interested in that have nice properties for CAD/CAM applications. Talk about Hamilton and his invention of the quaternions, which came accidentally. We'll briefly describe the fundamentals of the quaternion algebra, and then we'll get to what quaternions are really useful for. They are useful for describing three-dimensional rotations. They give the most compact and intuitive way to describe rotation in 3 dimensions. We'll then discuss the history of what was essentially a ferocious battle between vectors and quaternions. This is a battle that the vectors won, obviously. But it was really very unfair. It was not fairly fought. We'll also discuss a little bit about 4-dimensional geometry because quaternions are useful for describing rotations in 4 dimensions. And 4-dimensional rotations are very strange transformations. They're completely counterintuitive. If you try to extrapolate what's going on in 2 and 3 dimensions to 4 dimensions, you don't get a proper idea of what's going on at all. If we have time, I'll finally discuss a little bit about the generalization of all these techniques known as Clifford algebra. Here are some sources. Hamilton's original writings, 1853, 1866. And here, sitting on the shelf in Shields Library, is the worst possible place to learn about quaternions. Hamilton's Elements of Quaternions. This is the original 1866 copy here. This book is about 40 years older than UC Davis. And You can see it has not been a very popular book. The last time it was borrowed from the library was about 10 years ago, in 2003. The reason this is the worst possible place to learn about quaternions is that Hamilton himself didn't really understand what was going on. For example, he tried to describe a rotation, a three-dimensional rotation, using a one-sided multiplication with a quaternion. You now know you require a two-sided multiplication on the left and on the right. This book is a history of the origins of vector analysis, describes the fight between, on the one hand, the mathematicians, on the other hand, the physicists and engineers. The mathematicians lost this battle. But it's a very interesting study in the evolution of scientific ideas. It would be nice to think that a kind of Darwinian process occurs in scientific research, where the best ideas always win out. It's not necessarily the case. There are fads and fashions in scientific research, just as there are in other walks of life. There has been an upsurge of interest in quaternions in recent years. You see applications to computer graphics and animation. Here's a recent book, Quaternions and Rotation Sequences, with applications to orbits, aerospace, and virtual reality. These two titles are quite heavy going. This is written by a mathematician, this by a physicist, but these are very authoritative sources. If you want a very gentle introduction to the topic, this book has just 5 pages. They're very easily understood. The nicest and most accessible introduction to quaternions I've come across. Again, here is a title concerned with applications to computer graphics. Now, you're all familiar with Pythagoras' theorem. There's the square on the hypotenuse, the sum of the squares on the other sides. If A, B, C are real numbers, we can pick any values for A and B, compute C like this. If we wanted the sides to be whole numbers, 3, 4, 5, for example, then we cannot pick A and B arbitrarily. There is a certain set of solutions to this Pythagorean equation in integers, and they can be characterized in this manner. So this condition is satisfied if and only if A, B, C have this structure in terms of other integers, U, V, W. And this structure of solution carries over to polynomials. So if we want a solution to a Pythagorean equation in polynomials, in other words, the sum of the squares of two polynomials is a perfect square of a polynomial, we need to have this structure. A, B, C are given in terms of other polynomials, U, V, W. The idea of a Pythagorean-hodograph curve is to marry this concept to the hodograph of a parametric curve. We are driving down this path here. At each instant in time, we have a velocity vector. Translate all those velocity vectors so they emanate from a common origin, and their tips will trace out a certain curve called the hodograph of the original curve. So we want to construct a curve such that the x and y components of the hodograph are elements of a Pythagorean triple. In other words, the sum of the squares is the perfect square of some other polynomial. And so this is the basic definition of a Pythagorean-hodograph curve. The elements of the derivative are satisfy Pythagorean condition in polynomials.
Why you want to do that?
Why? Oh, I'm about to say that. So this gives the curve some very nice computational properties. If you consider a curve displaced from a given curve by a certain distance d in the direction of the unit normal, that's called an offset or parallel curve. This curve becomes a rational curve. It is a curve that can be represented exactly in, for example, a CAD system. The parametric speed of the curve, in other words, the derivative of arc length with respect to the parameter, is a polynomial function. And this means that when you integrate it, you get a polynomial arc length function. So these curves have the property that you can measure the arc length precisely. You do not need a numerical quadrature. Okay? The bending energy, if I take an elastic object like this and I bend it, better not bend it too far because it will go beyond the elastic limit. The amount of energy that's stored is proportional to the integral of the square of the curvature with respect to arc length. This integral has a closed form solution for these curves. You can minimize the energy integral subject to interpolation constraints and get what are called fair curves. You can drive computer numerical control machines along curved paths using the analytic description of the exact curved path. You don't have to approximate with what are called G-codes. Later on, I'll talk a little bit about rotation minimizing frames. So in the planar case, we define the components of the derivatives of a planar pH curve in this manner, integrate to get the curve, and you can construct these curves. Here are examples shown in the blue. They solve a first-order Hermite interpolation, initial point and derivative, final point and derivative. And here we compare them with the red curves, which are the ordinary cubics that are solutions to this problem. You can see that the curves have nicer shape properties. So, for example, this data implies an inflection. The cubic leaves it too late to turn around, produces a very sharp spike in curvature. The Pythagorean-hodograph curve gives a much nicer shape. So we have a model for achieving this construction using complex variables. We take a complex polynomial, w, u plus iv, and if we simply square it, we will automatically get u squared minus v squared for the real part of the square, 2uv for the imaginary part. So complex numbers give us an algebraic model for constructing these planar pH curves. Later on, we'll see that the quaternions are what we use in the context of spatial curves. You can construct also spline curves, which interpolate discrete data in a curvature continuous manner. Again, the blue is the pH curve. The red is the vanilla cubic spline. This is what you'd get if you construct an interpolating curve in any CAD system. It is known the cubic spline has bad shape properties, spikes in the curvature at the interpolation points. Okay? pH curve gives a much smoother curvature profile. You can design curves with control polygons. So by moving the vertices of the polygon around, you manipulate the shape of the curve. You can see that the pH spline and the cubic spline, blue and red, are virtually indistinguishable. I mentioned that the offset curves are rational curves, exactly representable in the CAD system.